The manufacture of carbide cutting tools is an exacting process. Raw materials required for the production of these tools are extracted from ore. The base materials used are tungsten, titanium, tantalum, and niobium ores. Tungsten-bearing ore has very little tungsten content. By crushing and separating, it's possible to obtain a tungsten content of over 50%. The crushed and separated ore is then further refined and converted to tungsten carbide powder with a consistency close to that of talcum. The powder is then combined and mixed with various additives. These additives give the tungsten carbide the desired properties required for differing uses. The additives also make it possible to form the powder, making it easier to handle and converting into solid shapes. The forming is usually done in mechanical presses, where the powder is pressed into shapes approaching that of the end product. At this point, the product is referred to as being in its green state, meaning it has not yet been consolidated by heat, or as we call it, sintered. In some instances, the product is pre-sintered at temperatures up to 1200 degrees Fahrenheit. This process hardens it to the consistency of chalk. In this state, it can be machined before final sintering. The sintering process reaches temperatures of over 2500 degrees Fahrenheit and causes the carbide to shrink, a critical but carefully considered step in the manufacturing process. Once sintering is completed, it is sometimes necessary to finish grind the carbide. Here, typical grinding operations take place in the insert manufacturing process. The last operation is coating. Two processes are commonly used, CVD, or chemical vapor deposition, and PVD, physical vapor deposition. In the CVD process, inserts are loaded onto tungsten rods in graphite trays and are heated to 1900 degrees Fahrenheit in a hydrogen atmosphere. Then, at a pressure of 0.1 atmosphere, reactive gases are introduced to deposit the initial coating layer. The gas mixture is changed to deposit each succeeding layer. For example, titanium tetrachloride and methane are used to deposit titanium carbide, while aluminum chloride, carbon dioxide, and hydrogen chloride are required to deposit aluminum oxide. Even though they are less than 1/1000th of an inch thick, multi-layer CVD coatings improve wear resistance and provide longer tool lives and higher speed capability. Two processes, ion plating and magnetron sputtering, are in common use for depositing PVD coatings. In ion plating, the metal component of the coating is evaporated from a metal target by a low-voltage arc, while in sputtering, the metal atoms are removed from metal targets by bombardment with argon ions. At the same time, a reactive gas is fed into the coating chamber to provide the non-metallic component of the hard coating. The ionized metal and gas atoms are then accelerated against the tools by an electrical field. On impact, they are deposited as a thin coating with a desired composition. Because PVD is a line-of-sight process, to ensure uniform coating thickness, tools and rotating fixtures are passed through the ion plasma or cloud created by the arc or argon-bombarded targets. The type of material being machined determines the grade of carbide to be used. Different workpiece materials produce different types of chips. Flowing continuous chips are produced by steel. Segmented broken chips are produced by cast iron. When cutting steel, the resulting continuous chip causes both top and edge wear on the insert. Discontinuous chipping materials, such as cast irons, are more apt to cause edge wear because the chip breaks before flowing across the top of the insert. Now, you probably realize that the manufacture of carbide cutting tools is a very complex process, requiring many different steps, and quality is a critical ingredient in each step. Today's global manufacturing demands continually improving reliability, consistency, and performance from its tools.